So in this third video, we're going to go in just a little more detail about how matrix multiplication works. We're not going to actually ask you to do matrix multiplication, but just understand some general properties. And in addition, we're going to talk about the transpose operation that can be performed on a matrix, and you will be expected to do that. So what can we say about matrix multiplication? Well, just think about the example that we just did. We know that you can multiply a matrix times a matrix, particularly if that second matrix is a vector, if it's only in one dimension. We saw how the coefficient matrix times the unknown vector gives us another vector. However, what happens is matrix multiplication, unlike kind of scalar numbers, it isn't always defined. If I give you any two numbers, you can always multiply them. It might be hard, you might need a calculator, but that result exists. In addition, if I ask you to multiply any two numbers, you can change the order in which you enter the numbers in your calculator. You get the same answer. Multiplication commutes. That is not the case with matrix multiplication. In fact, in general, if you pick two arbitrary matrices, you probably can't multiply them together. So under what conditions can you actually do the multiplication? Well, if you have two matrices A and B, and A has I rows and j columns, and B has m rows and n columns, you can multiply them together if and only if j equals m. So let's think about what that means. The number of columns in the first matrix equals the number of rows in the second. And if that is satisfied, you're going to get a new matrix, and it's going to have I rows by n columns. So the way that I think about it is, if the inner dimensions match, the resulting product is going to be a matrix that takes on the outer dimensions. So if j and m are the same, you get an I by n matrix. In any other case, you don't necessarily get a product. It's not defined. So just to check, does this hold for our 2 by 2 system of equations we discussed in the previous lecture? Well, think about it. The coefficient matrix there was 2 by 2. The unknown vector was 2 by 1. So the 2's match on the inside, and we should get a 2 by 1 on the outside, which we did for our constant vector. Just to show you what I mean by that, let me back up here. What I was basically saying is, it would help if I didn't go too far back. Here, you have a 1, 2 row by 1, 2 column, a 2 by 2 matrix, being multiplied by a 2 row by 1 column vector. So a 2 by 2 times a 2 by 1, since the inner 2's match, will be 2 by 1. So that is exactly as we would expect. So what does it say about implying? What does it say implying about the commutative property of multiplication? The commutative property doesn't exist. You can't change the order of the matrices being multiplied and expect to get the same result. In fact, the majority of the time, you won't even be able to do the product. So let's think a little bit more about that 2 by 2 matrix vector system that we talked about earlier. So we said we could write this as the 2 by 2 coefficient matrix, when multiplied by the column vector, gave us another column vector. Well, let's think about how this actually came about. Remember, it came about from the actual original equations. And just writing them in a little bit different order, what that means is we're going to get the constant k1 if we take and we multiply the coefficient of x, which is a, times x, plus the coefficient of b, times y. So if you notice, this is just a different way to write that original equation. I just swapped the order of it. But you can think about really what's going on here. The way that you're getting ax plus by is you're taking this first row of the coefficient matrix, which is a and b, and multiplying it by the unknown column. And that's exactly what is going on. You're taking a 1 row by 2 column and multiplying by a 2 row by 1 column. So that must tell you, the point of me showing you this is to show you how multiplication is defined when you have a row vector times a column vector. You just kind of do it in the natural way that you would think. You take the first elements and multiply them together, you take the second elements and multiply them together, and you add them. And this is going to be an operation that you're going to see very often throughout the remainder of your engineering career. And it takes on a lot of different names. Sometimes it's called an inner product, sometimes it's called a scalar product, sometimes it's called a dot product. The scalar product is the one that we're going to kind of focus on the name of. And think about why that is. You're really taking a row vector times a column vector, and you're getting just a scalar. That's why that is called a scalar product, or in this case, an inner product. It turns out when you go on to your matrix algebra class or linear algebra class, you'll talk about how there's another way that you can multiply vectors times vectors and actually get matrices, and that's called an outer product. But if you think about it, if you wanted to write a dot product to two vectors in general that were both row vectors, what you're going to need to do in order to make the dimensions work, if they're both row vectors, because notice up here, it was a row vector times a column vector, you're going to need a way in order to flip and make the row vector a column vector. And that operation is called the transpose. So I just wanted to make you aware of that because it's something that shows up all the time in engineering math. The transpose operation, if you apply it to a vector, is going to make a row vector a column vector or a column vector a row vector. if you apply it to a matrix, it's going to take each individual row and make it a column in a new matrix. Alternatively, the same thing, you can take each individual column and make it a row. And we'll see in an example here that process actually happens. So thinking back to that system of equations that we worked on in the last module, remember that when we did our actual solution, this is the result that we got. The coefficient matrix at row 1 was 1, minus 2, 0. Row 2 was 4, minus 3, 2. Row 3 was 0, 0, 2. So if I want to take a transpose of that, what I need to do is take the first row and create a new matrix where that row is the first column. Take the second row, 4 minus 3, 2, and create a new matrix where that is the second column, 4 minus 3, 2. Take the third row, 0, 0, 2, and in the new matrix, make that the third column. So first row becomes first column, second row becomes second column, third row becomes third column. You alternatively, look at it just really quickly, don't confuse yourself, could do it the other way. You could take the first column, 1, 4, 0, and make it the first row, 1, 4, 0. Same thing for the second column, minus 2, minus 3, 0, becomes the second row, and so on. So just note that you can do that in either way, but the key point here is that what the transpose operation is doing is it's taking and creating a new matrix where the rows in the new matrix were the columns in the old matrix, or vice versa. So you'll get a chance to do that in the actual homework. Just know that you can do it either way, but it probably is easier to just pick one and focus on that.